Hey everyone, I hope you're doing well today. In this video, I'm going to go over 10 different practice problems dealing with negative and zero exponents. Let's jump right into it. For this first example, let's try a fraction where we have this 2/7, and we're going to raise it to the negative second power. So if we ever have a fraction raised to an exponent, keep in mind that you can rewrite this as the numerator written to that exponent, as well as the denominator raised to that exponent. Okay, so this is the same thing as 2 to the negative 2 power and 7 to the negative 2. If you want to rewrite a power using a positive exponent, you're supposed to move the numerator down, and you can move the denominator up. So what happens if you move those is, if you write the 7 to the negative 2, if you move it to the top, that becomes a 7 to the positive 2. And for the 2 to the negative 2 moving down, it's going to be 2 to the positive 2. If you go ahead and now evaluate this, 7 to the second power is going to be 49, and then 2 to the second power is going to be 4. You can also rewrite this as a mixed number if you'd like to. 49/4 is fine, but you can also write 12 and 1/4. So in terms of an answer, you can either write it like this, writing it with the improper fraction version, or you can write it like this for the mixed number version. For a second example, let's go ahead and try a power to a power. So for this one, I'm going to write, let's try 2 to the negative 1 raised to the fifth power. Okay, so keep in mind that when you have a power raised to a power like this, so it's 2 to the negative 1 to the fifth, you can actually just multiply these powers together. So this is the same thing as 2 to the negative fifth power, since negative 1 times this 5 is equal to negative 5. Then if you want to write this using a positive exponent, just like in the first example, we can write it as the reciprocal and write it as 1 over 2 to the fifth. Now it has a positive exponent if you move it down, and this is going to be 1 on top. And then 2 to the fifth power, that's 2 times 2 times 2 times 2 times 2. I think I said the 5 2's there. That would be 32. Okay, so that would be number 2 here. Let's try another one. Let's go ahead and try this one where we have 16 times the quantity of 2 to the negative third power, and let's put that over 2 to the second power. Okay, so if you're not sure what to do with these types of problems, keep in mind that as long as we have the same base, so we have this 2 and 2, same base, and we have a fraction here, what we can do is we can take the numerator's exponent and subtract the denominator's exponent. So we can say this is the same thing as 16 times 2 to the negative 3 minus 2 power. Okay, so whenever you have a fraction and you have the same base, you can subtract their exponents if you are in a fraction or dividing. So we can say this is 16 times 2 to the negative 5 power, since negative 3 minus 2 is negative 5. Okay, and then going from there, what can we do? I think what I want to do is right here, write 16 times, and keep in mind that 2 to the negative fifth power is the same thing as 1 over 2 to the positive 5 power. And then what is 2 to the fifth power? I think we did that in the last example. That's 1 over, and that's 32. Then you can cross cancel the 16 and the 32. 16 goes into 32 2 times, and so that's going to end up just being 1/2. There's our answer. For this next one, let's try another practice problem dealing with these negative and positive exponents with fractions. So let's do 4 times this 3/2, and let's raise that to the negative first power. Okay, so what we can do here is keep in mind that we can write this 4, and this is going to be times, and then this is going to be 3 to the negative 1 power, and on the bottom we're going to have 2 to the negative first power. So we can split that exponent and give it to the numerator and the denominator. We like having positive exponents. We're going to move this one down, and we're going to move this one up, move the entire power there. So if that happens, then we have 4 times, and it's going to be 2 to the first power on top, and 3 to the first power on bottom. Now they're positive since we moved them. And then 2 to the first and 3 to the first are just 2 and 3. So this is really 4 times 2/3. And I don't think we can do any cross canceling, so that'll be 8/3, also known as 2 and 2/3 as a mixed number. So either one of these is okay. I guess I'll just box these together. They're just different forms of the same answer. All right, here is a fifth example. Let's try using some variables now. So for number 5, let's try the quantity of negative 11h, and let's raise that to the negative second power. Okay, so Now we have variables, but don't worry, they work very similarly, and I think they're a little bit easier, to be honest, just because we don't have to evaluate them. And so if we want to rewrite this using positive exponents, we need to go ahead and reciprocate. So we're going to write 1 over negative 11h, and that whole thing is raised to the positive 2 power, right? So whenever you want to write a negative exponent using a positive, make sure we reciprocate. And what does this really mean? Well, the one on top just stays the same. This is negative 11h times negative 11h. So this is really negative 11 raised to the second power, and it's also h raised to the second power. So what's negative 11 times negative 11? That's positive 121. And h squared is just h squared. So like I said earlier, it's actually kind of easier because you don't have to actually solve that because we don't know what h is. But we do know if we knew what it was, then we would just square it. Okay? So there's the 5th example. And let's try another one. Let's try something a little bit more complicated using these variables. Maybe use a fraction as well. So let's try, in the numerator, we'll have 3x raised to the negative 3rd power. And let's multiply that by y to the 4th power. Let's put that whole thing on top of negative x squared times y to the negative 6th power. Okay, so if you have something like this, what we would do first maybe is we would just do one part at a time, so we can look at this first part in the numerator. So starting off by just looking at this 3x to the negative 3rd power, let's see how we can rewrite that. Well, we can actually move that whole thing down to the denominator just because it has a negative exponent. So, and we could also actually move this y to the negative 6th power to the numerator since it has a negative exponent, right? So let's go ahead and do that. In the numerator, we're going to have this y to the 4th power. That's going to stay the same since it doesn't have a negative exponent. But when we move this y to the negative 6 up, that's going to become y to the positive 6th power, y to the positive 6th power. Now, for the bottom, keep in mind that we still had this negative x squared that we didn't touch. That stays down there. It has a positive exponent, so we don't have to do anything with that. And then moving this whole thing down, what we get is we are going to multiply this whole thing by this 3x raised to the negative, well, if we move it down, it's to the positive 3 power. Don't want to make that mistake. The whole point of moving it is to now make it have a positive exponent. Okay? In the numerator here, if we go ahead and multiply y to the 4th power times y to the 6th power, that's really just y to the 10th power. Okay? That's because you basically have 10 y's being multiplied together. In the denominator, we have this negative x squared that we didn't touch, and then 3x to the 3rd power, that's 3 times 3 times 3, so that's going to be 27. And then x to the 3rd power is just going to be x to the 3rd power. So I'm going to make this a little longer since I had a lot more going on down there. And then in the numerator, we still have this y to the 10th. We can't really do anything with that. But in the bottom, 27 can be written first as a coefficient, and there's a negative from the negative x squared, and then x to the 2nd times x to the 3rd is going to be x to the 5th power. So we're just multiplying the numbers together, so negative 1 and 27 make negative 27, and then the x to the 2nd times x to the 3rd is x to the 5th. Here's another one. Let's try simplifying down this expression where we have 12x to the 8th power times y to the negative 7th power. Let's put that whole thing on top of 4x to the negative 2nd power times y to the negative 6th raised to the 2nd power. Okay, so first things first, what we can do here is make sure the denominator and the numerator, each of them kind of, let's see what we can simplify. And so the numerator, there's not really much anything we can do right now. The bottom actually looks more complicated to me, just because it has like parentheses and everything's grouped up. So keep in mind that this little 2, right, this little 2 actually belongs to the 4, that base. It belongs to the x, and it belongs to this y. So make sure they all get that. So 4 to the 2nd power is going to be 16. Whoopsies. Is going to be 16. And then x to the negative 2nd power to the 2nd power, you just multiply those exponents. So that's negative 2 times positive 2 is negative 4. And y to the negative 6th to the 2nd power, that's negative 6 times 2. That's going to be y to the negative 12th power. So if you need to pause to think about that, go ahead. But if that makes sense, hopefully you can think through that and replay if you need to, if that's helping to make it more clear. Okay, so now the bottom doesn't have parentheses, so it's a little bit easier, I think, to deal with. And there's different ways to kind of go about this next step, but how I'm going to show it right now is let's take anything with a negative exponent and move it. So again, this one has a negative exponent, so we can move it down to the denominator, so it'll have a positive exponent. But this x to the negative 4 has a negative exponent down here, so let's move it up. So it's becoming x to the positive 4. And we can also take this y to the negative 12th power and move it up so it has a positive exponent as well. So let's see what happens if we move everything. So this is going to be 12x to the 8th. That stays because they have positive exponents. And then the x to the negative 4th is going to come up to become x to the positive 4th. And then that y to the negative 12th is going to move up to become y to the positive 12th power. In the bottom, what did we have that didn't move? I think it was a 16 stayed put. And then what moved down? Anything? That y to the negative 7th moved down to make it y to the positive 7th power. Okay, so the whole point of what I just did there was I wanted to make all the exponents positive. And there are other ways you could subtract the powers if you need to, but I think this is a little bit more clear just to kind of get started. Now if we're going to go ahead and see what the GCF is from the numerator and denominator to simplify this fraction, it looks like for 12 and 16 you could divide them both by 4, and so that would be 3, and then that would be 4 for the coefficients. And then you can also see here that they both have y's. This one has 7 of them, but this one has 12. So if they cross out what they have in common, they both have 7, then there's still 5 left on top. Okay, so I think that's it, and I think we can combine something in the numerator, right? So we can go ahead and combine this x to the 8th times x to the 4th, and when we do that, let's see what we have left on top. We have a 3 as the coefficient, then we have x to the 12th power, and then we have the y to the 5th on the end, and that's all over 4. I think 4 is the only thing left in the denominator, so that's it. Let's try a few more examples here. So get some space. Let's go ahead and delete some of these things here from earlier. I'll go ahead, I think we were on 7, right? So let's try an 8th example. This time let's try to see if we can figure out whether some statements are true or false and provide some examples or counterexamples. So let's do a to the negative 3rd power over a to the negative 4th power. And the question is we're going to put this equal to 1 over a. I want to know that if this, as long as a can't be equal to 0, all right, let's say a is not equal to 0. My question is does this work for all values of a as long as a is not equal to 0? So a can be positive, a can be negative, a just can't be 0. I'm wondering if this is true for all non-negative values for a. And if it's not true, let's provide a counterexample. Let's prove why it doesn't work, okay, or show why it doesn't work. So what I would do first here is I would actually simplify the left side, move that up and move this down because they have negative exponents. So why not write this using a little bit more clear approach? So that's going to be 4a to the 4th power over a to the 3rd power. And again, this is equal to 1 over a, so this is still the same statement or the same equation. And then what we can do is we can subtract exponents here. And we can rewrite this as a to the, on the left side, this is really a to the 4 minus 3. Remember, as long as they have the same base, you can do that. And 4 minus 3 is 1, so this is really just a on the left side, a to the 1st power, a. So the question is, a equals 1 over a. So let's say, for example, if a was equal to 1, right? So if a equals 1, is this true? So if a is equal to 1, we would substitute 1 in. We would have 1 is equal to 1 over 1. And 1 over 1 is 1, so this seems to check out, right? So does that always work? Well, what if, let's say, a is equal to 2? Well, then the left side would say 2, and the right side would say 1/2. And is that true? Well, I don't think that's true because 2 does not equal 1/2. They're reciprocals. So that doesn't work. We can try another positive value, like what if a is equal to 5? Well, then it would say 5 is equal to 1/5. You gotta ask yourself, is that true? Well, I don't think so. So we're gonna go ahead and say that's not true. And then maybe we can go ahead and try a negative value. So let's say if a was equal to negative 4, just to test it out. And so we'd have negative 4 and say, is that equal to 1 over negative 4? Well, that's also going to be a no, just because they are reciprocals again. So the question is does this work for all non-zero values of a? And so your answer to this is going to be no, it does not, right? We just proved that, well, it does work for 1, it doesn't work for other values of a that are non-zero. So we can conclude that this does not work all the time. Let's clear up a little bit of space and just try 2 more examples here. So for a 9th example, let's go ahead and try another similar logic kind of question dealing with seeing if we can prove or disprove something. So a to the negative first power plus b to the negative first power, and say, okay, that's equal to 1 over a plus b. And again, here I'm going to say that a cannot equal 0. And I'm also saying that b cannot equal 0. So we're just talking about values where a is positive or negative and b is positive or negative. So let's see if we can prove that if this is true 100% of the time. So for this first one, a to the negative first power, remember we can rewrite that as 1 over a to the first power, but actually let's just write a. I won't write the exponent. And then for b to the negative first power, we want to know that's the same thing as 1 over b. And so the question is that equal to 1 over a plus b? Is it equal to that 100% of the time? Well, if we really wanted to write the left side using one fraction bar, because notice how there's 2 fraction bars on the left, we would need common denominators. So the GCF here would be AB. So we'd multiply this side by b over b and multiply this fraction by a over a. So if you did that, we would get b over ab plus, and 1 times a is going to be a over ab, and that should be equal to 1 over ab, if this is true. Now that we have common denominators, we can say this is going to be a plus b over ab. And we're wondering, is that always equal to 1 over a plus b? And so we can try to prove or disprove this using some different values here. So let's see if this actually works. So if we do some examples, some hypothetical values, what if we said like a was equal to like 2, and we can say like b was equal to like, I don't know, 6, right? So if we did that, what would happen? So on the left side, we'd have 2 plus 6. We'd have 2 plus 6 over 2 times 6. And is that equal to 1 over 2 plus 6? So 2 plus 6 on the left side is going to be 8. 2 times 6 is 12. So is 8/12 equal to 1 over 8? And I'm pretty sure that's just not true, right? Because 8/12 is a much bigger fraction than 1/8. So there is an example of disproving it. So this right here, I know in number 8 I showed a few different possibilities, but once you disprove something one time, you know it never works. Sorry, not that it never works. You know that it can't work 100% of the time. Okay, so this is called a counterexample. We just showed that if a was 2 and b was 6, that this rule breaks if they're saying that these are true, but it turns out it's not true. So you can test out more examples if you'd like to, but it does not work. And here's one final example. I'm going to go ahead and try to squeeze this over here to the right. So the mass of is just 1 grain of salt. So the mass of 1 grain of salt, let's just say that's equal to 10 to the negative 4th power grams. So you can imagine 1 grain of salt is going to be very, very light. And so I'm wondering how many grains of salt are going to be in a box that has 100 grams. So that's for 1 grain. I'm going to go ahead and write that here. That's 1 grain. And then for 1 box, let's go ahead and label that 1 whole box. That's going to be 100 grams. So the question here is how many grains of salt are going to be in this box? Well, let's try to talk about the 1 grain first. So the 1 grain, we said is equal to 10 to the negative 4th power grams. So what does that really mean? Well, 10 to the negative 4th power, we know that we can rewrite that as a fraction and say that's 1 over 10 to the 4th power of these grains, right? And what's 10 to the 4th power? That's going to be 10 times 10 times 10 times 10. So that's going to be 1 over, let's see, 110 is 10, that's 100, that's 1,000, that's 10,000. So 1 grain of the salt is going to be 1 over 10,000 grams, right? So it's very, very small. So the question is how many of these things, right? How many of these 1 over 10 thousandths of a gram fits inside of these 100 grams? Okay, so if you want to see how many of those fit inside there, well, think about it. You do need 10,000 to fit into just 1 gram. So to fit into 100 grams, you need 100 times that value. But I can also show it to you this way as well. So if we want to see, okay, we have 100 total grams, and we want to see how many times this 10,000 fits inside, then hopefully it makes sense. We're going to divide, right? Because if you want to see how many times something fits into something else, you need to divide. So we can rewrite this as, if we do a little keep change flip, we have 100 times, and it's going to be 10,000 over 1. If you keep change flip. So this is really just the same thing as 100 times 10,000. So if you do 100 times 10,000, if you multiply by 10, that's 100,000, and you multiply by 10 again, that's going to be 1,000,000. So that's going to be 1,000,000 grains. That's how many would go into that 100 grams of salt. And there you go. There you have 10 different practice problems helping you practice working with some zero and negative exponents. So hopefully you found that helpful, and good luck, and I'll see you next time.